Hi, my name is Daniel Rogge. I'm a control engineer for Tormach, and I'm one of the lead developers on the PathPilot software. Today we're going to go over the Chapter 4 in the lathe manual, Introduction to the Control Software, and making your first part with the Slant-PRO Lathe. First thing I'm going to want to do is reference the machine. So I'll click the Ref Z button, the Ref X button. So now the machine's referenced, we can go ahead and jog the machine around a bit if we wanted to. You notice this particular lathe is equipped with an enclosure and with an 8-position turret for automatic tool indexing. Some of our other lathes would have just a chuck guard and could have a manual tool post or gang tooling. But we're going to do this demo with the turret. So if we go over here to the manual, Chapter 4 is what we're going through. The workpiece you're going to need for this is a piece of 1-inch aluminum bar. We're going to be making a bushing for the turret here. So the turret has ID holders that would allow you to hold either an ID tool or a drill or a tap in it. And the ID holders have a 3/4 inch bore, but you might want to neck that down to, say, 1/4 inch for a tap or a drill bit, or maybe holding a boring bar. We do sell some inserts that will hold standard sizes like 3/8, 5/8, 1/2 inch, but for whatever reason you might want a bushing to make hold something special in there. That's what we're going to be making today with first part. So we'll take our 1-inch piece of aluminum stock, and we want this to protrude from the well, if you're using a collet, protrude from the collet by a couple inches, or if you're using a chuck, you want it to protrude from the chuck by a couple inches. We sell a nice little tool made by Stop Lock, so I've set this to 2 inches. And I'll go ahead and make sure that that guy's coming out about 2 inches there. Now I've got some examples of some other materials here. If you don't have aluminum, if you only have brass or steel or even stainless steel, you can go ahead and follow the same instructions. The feeds and speeds in this are not too aggressive, so actually with a carbide insert you probably get away cutting almost anything with the feeds and speeds recommended in this tutorial. But for today we got a piece of 1-inch aluminum. The tools you'll need 2 tools. You'll need a right-hand turning tool. That's the one we're using. Is part number is 33131. But any right-handed turning tool should do. And then you'll need a cutoff tool. And for the purposes of this tutorial, we're going to put the turning tool into position 1 in the turret, and we're going to put the parting tool into position 2. And I'm going to jog the turret down a little bit just to make things easier on myself here. For the purposes of this first part tutorial, we're going to use the right-handed turning tool as tool 1. So let's go ahead and put that in the turret. Now, we already have a tool here in position. Looks like someone left a threading tool in position 1. We'll go ahead and remove that. If you've never had experience with a lathe turret before, the tools are locked in with these wedge-style clamps. And it's such a positive retention. Even after loosening the clamp, you can't get the tool out. This center screw here is actually the release screw, so you have to bring that one in to undo the clamp. There's one other really important thing to mention here, and that is that this clamping system is reversible. So in this position here, I've got a tool mounted such that the insert is facing down when we're cutting. And that's the normal cutting position for this lathe. But if you've just bought a machine and you've just set the turret up, to shim the turret, we have requirement that the insert's facing up so you can see the size of the pip. And for the insert facing up, this clamp would be on the other side. Once you're done with that shimming the turret operation, you want to make sure that all your clamps are down on the lower side of the pocket, which allows you to place the tool in with insert facing down. So to place our right-handed turning tool in there, I'm just going to go ahead. Notice I loosened up on that release screw, and I'm just going to go ahead and tighten these 2 guys. And it's in. Looks like turning tool is tool 2 here. We'll go ahead and put this one in. Again, insert face down. We have our right-hand turning tool in pocket 1, and we've got our parting tool in pocket 2. So that covers the workpiece preparation and the tooling preparation. Now we're going to go ahead and set the work offsets and the tool length offsets for this part. I went ahead and kind of set this machine back to the state that you'd find it in if you had just purchased a machine and just brought the computer up for the first time. So if we go over to the offset screen, it so happens we're at tool position 3. That just made it easy for me to access the pockets for 1 and 2 to put those tools in there. If we go to the offsets table, you'll see the tools 1, 2, all the tools here have no X and Z geometry offsets. They've got no wear offsets. The nose radius is standard for the ones that we sell. And over here, G54 work offsets for X and Z are 0 and 0. So a lot of times people ask the difference between a tool length offset and a work offset. And in mill, it's a pretty simple answer. The tool length offset is the length of the tool from the control point, the tip of the tool, to the shoulder of the tool holder. But on a lathe, it's kind of a different story. It's a little bit more complicated because you have not just a Z tool length offset like on a mill, but you also have an X geometry offset. So if we're taking a look at the turret here, a lot of times when I'm teaching a class or talking about tool length offsets for lathe, I'll ask people what they think intuitively the length of one of these tools is. And a lot of times the answer I get is, well, maybe the length of this tool is the distance that it sticks out relative to the face of the pocket here. So this would be the offset in Z, and this would be the length offset in X. And if all you're using is turret tools, that's not a bad way to think of tool offsets. As soon as I mount some tools here on a gang post, though, that becomes a little bit more problematic, because then my X offset for a gang tool would be the distance between the turret pocket face and the gang tool's tool tip, which is kind of a nonsense distance. What's really important are that all the tool distances, the control point distances, are correct relative to each other. So the entry in the tool table is correct relative to all these tools. And there are a few ways that we can achieve that. If you're only going to have tools in a turret, a really popular way of doing it is to make a setup block, which is an L-shaped block that you can set up against the face of the pocket. And this L-shaped block would allow you to slide the tool up until it made contact with the top face of the block. And that way all of your turret tools you'd position, and they'd all have the same length. And that's pretty nice because when you add a tool to the system, you don't have to go touch the thing off again. You might change the wear offset by a few tenths, but for the most part it's a pretty repeatable way to do it. So if you have a setup block on a turret, using this distance as a true tool length is a good way to go. But if you're using quick change tooling, or especially if you're using a combination of gang tools and turret tools, thinking of the tool length as a true distance from a reference surface to the tool tip doesn't work as well. What we're going to do here is use the idea of a master tool. We'll call tool 1 the master tool, and what we're going to do is we'll take a skim cut of the workpiece. We'll use that skim cut to set the work offset for both the diameter and the length. And then we'll index to tool 2, and we'll touch off tool 2 in a similar manner, except instead of using those skim cuts from tool 2 to set the work offset, we'll use the skim cuts for tool 2 to set the tool length offset. What that in effect does is it'll give us no tool offset for tool 1. Tool 1 will have a 0 length offset. The entire offset will be in the work offsets when it comes to tool 1. And tool 2 will have a small work offset, or a small tool length offset, and that tool length offset will be the physical difference between how far this guy sticks out and how far this guy sticks out. If that's a confusing idea, you're not alone. It may take watching this video a couple times to get the gist of it, but hopefully as we go through it and I point out some numbers on the screen, you'll see what I mean. So just for educational purposes here, I'm going to go ahead and re-reference the X and the Z axes. And it warns me when I'm doing this. It says, hey, Z is, like, X is already home. Do you really want to rehome? Sure. And I want you to notice, here we are sitting at the home position of the machine. That's the machine 0 position. That's where the machine thinks of everything from. And right now the X and Z DROs read 0, 0. The reason for that is that there's no value in the X and Z work offsets registers. If there were a value, then this would read something else. But there's no value here for the work offsets yet. So right now my DROs are actually reading out the machine coordinates. I'm going to go ahead and call tool 1 up here, and I've got to close the enclosure door to index the turret for safety reasons. So I'm going to go ahead and type T1 in there. In terms of the FANUC language for tools on a lathe, you can apply geometry offsets by taping a 1 or 2 digit number. So T1 will apply the geometry offsets for tool 1, or I can type TO1, will give you the geometry offsets for tool 1. The second 2 digits of a tool change callout will also apply the wear offset. So if I want the geometry offsets plus the wear offsets, I would type T0101 to get me geometry and wear offsets. And that'll also index the turret. So I want tool 2, I can say T2, or I can see T02, or 02, sorry. Or I can say T0202 if I want geometry and wear offsets. And that's in contrast to the mill. On a mill, if I want tool 1, I'd type T1M6, and T's tool 1 for preparatory move for tool 1, and M6 is change the tool. But to apply the offset, I then have to type in a separate G43H1 command. It's worth noting on lathe, there's no G43. Your offsets are always applied when you do a tool change call out. So tool 1 with offsets is T1. Tool 1 with geometry and wear offsets is T0101. So let's go back to tool 1 real quick. I'll just go ahead and do it with the geometry and the wear offsets. Now, my machine is still reading out 0, 0. And that's because if we go over to the offset screen, we'll see there's absolutely no tool offset. So I'm sitting at the 0 position, the machine 0 position, with no work offsets applied and no tool offsets applied. But of course, this doesn't correspond at all to where my part is. My part 0 is going to be the spindle center line. So let's go ahead and jog the machine closer to where I think my part 0 should actually be. And the first thing I'm going to do is just kind of eyeball this. And I'm really just doing this for the purpose of the tutorial. If I were actually setting these offsets, I wouldn't bother doing an eyeball. But right now, I just want to emphasize a point here. So if we look over here at where the tool tip is, you can see here that we're pretty darn close to Z0, which I'm at the end of the workpiece, we're calling Z0. And I'm pretty close to the edge of the diameter of the workpiece. It's a 1-inch bar, so I'm pretty close to X of 1 inch. Now this is a rear tool post lathe. Our slant bed lathe is configured as a rear tool post lathe, which means this is a positive number. It's positive X of 1 inch, right? If I were to approach it from this side with a front tool post, this would be negative 1 inch in X. So all these numbers are negative, and all those numbers are going to be positive. So let's go over here. We're still on the offset screen, and we see now that the diameter is negative 14 inches, and my Z is negative 6 inches. Just coincidental that it happened to be an exact number here. And we want the Z to be 0. So just remember, we've got, let's go over this offset screen here. Let's reset this tool. And it's a rear tool post right-hand turning tool. All right. So, and I'm just, once again, just eyeballing it. We haven't taken a skim cut. We haven't gotten exact, but I want to show you about the concept of work offsets. I'm going to go ahead and I'm going to tell the machine that we're actually at 1 inch away in the diameter. Right, so type 1, and I hit enter. And I'm going to tell the machine that we're actually at Z0, right? So we have 1 and 0. If we look back at our workpiece here, we can see we're at 1 inch in diameter, and we're at Z of 0, the face of the part, right? We're going to go over to the offsets table again. I just want to show you what happened when we did all that. So remember, we were at negative 14 or something in X, and we went to 1. And now we have an X work offset here in the work offset column. And that negative 7.5, this is actually, the machine is thinking of radial distance instead of diameter, but this is the number that was entered in when I typed 1 into that X diameter DRO. And then Z, remember it was negative 6 here before, and now we have negative 5.9999, right? So it's actually negative 6, just the machine's got a higher level of precision than we actually show to the operator here. And this work offset is applied. That's what allows me to think of this in terms of the workpiece. Now remember, there's still no tool geometry offset for tool 1. I can go ahead and put a description in if I want. Hey, this is our right hand turning tool. But I'm not going to use a geometry offset for this guy. We're going to apply a geometry offset for the parting tool. So this is just conceptually, we got close. Let's go ahead and do it accurately now. I'll take a skim cut and we'll see how close we got just by eyeballing it, huh? So I'm going to go ahead and turn the spindle on. We'll say, oh, I don't know, 1,000 RPM. And close the door. Even though we have an enclosure, it's always a good idea to wear eye protection. Turn the spindle on going forward. A little bit of run out on a workpiece. I'm going to go ahead and jog Z into the part. We'll just take a little skim cut there. Nothing fancy. Just enough to get a micrometer on. So you notice I'm backing up away in Z only. I haven't touched, not jogging an X at all. All right, let's go ahead and check the part. So this digital micrometer that we have here is a pretty handy little tool. It's something we sell. Very accurate, very easy to use. We're going to go ahead and measure this here. And 0.9056, 0.90555. So what we really were, 0.9056. So now we're quite accurate here after taking that skim cut. And the important thing to emphasize there was that we took a skim cut at a constant X. I didn't jog X while I was doing that cut, and I didn't jog X while I backed out of it. So it was at the same X position the entire time after I backed away from it. If I had moved X, then obviously I can't go typing in a value and expect it to be the same. So let's go ahead and we'll just go face off this part here. That's a really easy one. And I will start the spindle going forward. So here we are. We're going to jog it an X just to face the part off manually. And same deal, I'll move it away by moving it in X, but I'm not going to move it in Z here. And this is easy, you don't have to put a micrometer on it to figure out Z0, we're just going to click the Z0 button there. So now we have an accurate work offset set, and we're using that tool 1 as kind of the master tool. It doesn't have a tool length per se, because we've done the entire offsets from the standpoint of this tool. So just to reinforce, if we were to say, oh, rapid position move to X0, that would be spindle center line, Z of 100 thou away from the workpiece. Now when I hit enter, the machine will move over and we'll see it's going to move right to the spindle center line, 100 thou away in Z. All right, so we're going to go ahead and change tools. I'm going to jog it to a position that I feel like, oh, it's a safe tool change position. And we'll go over and we'll set our G30 position here. We're using the G30 position as a tool change position, and in our conversational code, when we generate conversational code, it'll always go to that G30 position. And if I jog the machine, I can press this go to G30 button, and it moves back to the G30 position. And we'll go ahead and change to tool 2. We can take a skim cut on X first, and we'll use that to set the diameter offset for this tool. A lot of chatter there. We're sticking far off the side of the workpiece. So we have 0.8969. Now I'm not going to type that value into the diameter DRO because that would set a work offset. This is not where we want to enter that 0.8969 value. What we want to do is touch this tool off here. We want to tell it it's a rear-mounted parting tool. And then we're going to touch X. This is going to set a tool offset. And what did I say it was? 0.89. Yeah, let me remeasure it real quick. 8968. 0.8968. I'm going to go ahead and enter that in the touch X. Now you can see the tool offset was automatically applied and it knows where we are. Then we'll go ahead and do something similar in Z. The control point for a parting tool, this is an odd one for some people. The control point for a parting tool is actually not the spindle side tip of the tool, it's the part side tip of the tool, because when you part off, you want, you care about the length of the part, not the length of the chunk left in the spindle. So what we have to do here to touch this guy off is we can go ahead and jog up to Z0 here. I'm just going to use a little piece of paper. Okay. And because the control point of that tool is actually the right-hand edge of the tool, like the edge of the tool that creates the part, not the edge of the tool that creates the chunk left in the spindle, we're going to want to touch this guy off, not at Z0, but at the thickness of that insert, which is 160 thou. We'll type in 160 thou, and we'll touch Z. So if you take a look here at where this tool is sitting, I'm saying that that side is going to be determining the 0 position. So our current position is Z of 160 thou, meaning if we were to go up, if we're going to go up away from the part here, and if I type in G0, Z0, what you'd see is if I were to part something off, I'd be parting it off at the 0 plane. Does that make sense? This is Z0 for the part. And this tool, as it parts this thing off, is going to part it off along that plane. So now I can go ahead and go back to G30. So we've gone through workpiece preparation. We have a 1-inch diameter bar that sticks out of the chuck by 2 inches. We've got our two tools, right-handed turning tool and a right-handed parting tool, both of which are mounted in the turret, positions 1 and 2. We've gone ahead and we've set the work offsets and the tool offsets for both tools. To be more specific, we set a work offset using tool 1 with no tool offset for tool 1, and then we went ahead and entered in a tool offset for tool 2. If we go to the offset screen here, the offsets for X and Z for tool 1 are 0 and 0, because everything for X for that tool is done in the work offset. And then tool 2, we have an X offset of 1.49 inches in diameter. That's the distance, the difference in length of the first tool and second tool, and a Z offset of minus 393 thou. And that would be the difference in how far this guy sticks forward to how far this guy sticks forward. We can go ahead and put a description in here if we want. All right, so now we'll flip forward here to writing the G code. So we're going to do this entire first part in the conversational code of the machine. Now the manual is written assuming a front tool post, so all the values that are in the manual are negative diameter values. So remember, it's a rear tool post lathe configured for rear tool post. That means all the X positions on the opposite side of the operator of the spindle center line are going to be positive. All the X positions on the operator's side of the spindle are going to be negative. This was written with a front tool post, quick change tool post in mind, so all these values are negative, but when we enter these in, they're going to be positive. So let's go ahead and code this up. Looks like the first operation is facing the part off, and we want to use tool 1. We're going to face it off. Looks like it's asking us to do minus 0.1 1, so 100 thou in. Initial X is going to be 1 inch. It's a 1 inch diameter bar. Final X is going to be 0. Sometimes people ask me why we have a final X, but of course if you're facing a tube or something that's already been bored out, you don't always need to go all the way to the center line. Z start here is 0, specified in the manual, and we know that the part doesn't stick out any further from that because we faced it off at 0 earlier. We'll give it a tool clearance of 100 thou, roughing depth of cut of 50 thou, finish depth of cut of 5 thou. I think you'd be fine with, even if you had steel instead of aluminum, you'd be fine with those values. It looks like roughing surface footage we've got set in the manual at 250, finish at 300. These are very conservative values. I know guys here that run stainless in these values and aluminum typically in the 800 range for these carbide insert tools. So we've got a chuck on this machine. I don't really like running a big 6-inch chuck much faster than a couple thousand RPM, so we'll limit our max spindle speed to 1800 RPM. Roughing inch per rev, that's your chip load, we'll say 10 thou. Finishing inch per rev, this will determine the surface finish on the thing, we'll say 3 thou. This surface feet might be a new one to some of you guys. A lot of people are used to programming spindle RPM if their background is in manual milling machine. The surface speed is something that equates the linear velocity of the cutter in a mill or of the workpiece in a lathe to the cutting edge of the tool. And in a lathe, it's much easier to think of a constant surface feet per minute than it is to think of an RPM, because if you think about it, as your workpiece gets smaller, as you're chewing through that diameter, you take a 2-inch diameter, turn it into 1 inch. Well, you'd have to spin the spindle faster on every pass to maintain that same surface footage. So on a lathe, typically you're programming in CSS, which is constant surface feet, constant surface speed, as opposed to programming in RPM. Similarly, typically on a lathe, we're going to program in terms of the chip load, which is feet per rev, not in terms of feet per inch. So it looks like we've got these values entered here, and we'll go ahead and press post to file. Oh, I forgot to retitle the thing. Let's create a new folder here. First part, and we'll call this guy face.nc. Now it should be loaded here in the control software. We can see the tool path. It's showing that we have the parting tool here now, but of course as soon as the program runs, it'll change to tool 1. So let's go ahead and run this code, shall we? First thing I always like to do is bring my max velocity slider and maybe even my feed rate sliders down to 0. Go ahead and hit cycle start. First thing that's going to happen is hit the tool change. And we see the spindle come on. And I'm going to start slowly inching my max velocity slider up here. And this makes it easy for me to go ahead and put a hold on things if anything looks wrong. So here it is. Right now I still have my feed rate slider turned to 0, which is why the machine is stopped. We'll take a look. And I kind of like doing a sanity check here. So we're stopped at feed rate of 0. The machine thinks that we're 1.2 inches in diameter and minus 0.0475 inches in Z. Let's go ahead and take a look here, see if that looks about right. It sure does. That looks right to me. I'm going to go ahead and bring up my feed rate slider and we'll go into the cut. There's my finish pass. Ordinarily, we'd have coolant on that as well, but for the purposes of the video, we didn't bother setting up coolant for the machine. So that's our first operation here. Let's go back and we'll do the OD turn on this. At the OD turn tab. We're using G54 work offset. Looks like that stuff is all the same for this. And tool 1. Z end of minus 1.6. Now as I cycle through these DROs, I'm just typing a number and hitting enter on the keyboard. Final X is 0.9375, 0.9375. No fillet radius, Z start minus 0.1. Oops, sorry. What did I miss there? Oh, I didn't enter my finished depth of cut. 0.005, 0.07 for my roughing depth of cut. So we've got everything looking like it does in the manual here. We could either create a new file here, or we could add this to our last file. We'll go ahead and add it to the last file. So now we see the toolpath display. We've got that initial face, and we come in and we do this, this OD turn. Now let's go ahead and we'll do the third operation. It's another OD turn op. Z end minus 1.25. Initial X is no longer 1. We already turned it down to 0.9375, I believe. Final X is going to be 3/4 of an inch. That's the ID of those little pockets in the boring bore, the ID tool holders on the turret. Looks like we're calling out no radius, Z start. Everything here looks good. So we'll go ahead and append that to the file. So now we have starting to look a little bit more like a bushing here. And operation 4, we're going to put a small chamfer on the part. So we'll go to the chamfer screen. We want tool 1 again, still using that right-hand turning tool. Z start is minus 0.1. Z end minus 0.15. Looks like we're putting a 50 thou chamfer on it. The X is going to be 0.75, right? Remember, if it were a front tool post, like quick change tool post, this would be minus 0.75, but this is a rear tool post. Chamfer angle 45 degrees, sure. Roughing depth of cut, manual says 100 thou. Finished depth of cut, 10 thou. And tool clearance, 0.1. And looks like everything else good to go. We'll go ahead and append that to the file. So now we've got that chamfer's been added. Looks like a couple passes there at the chamfer. If you want, we could get smaller with this, verify. Yep, it is. Is that what we think it is? And then the very last thing we're going to do here is part the workpiece off. That'll be pretty interesting without coolant. We'll see how it goes. Part screen here. And parting tool is tool 2. Initial X is going to be 1 inch. Final X, we're parting it down to 0. Z start minus 1.6. So the entire thing will be 1.6 inches long. That has to do with where we're touching off on the parting tool there. Surface feet per minute, calling out 300. Inch per rev, calling out 5 thou. No peck, no retract. Maximum RPM. This looks like we have 1800 in the manual, sure. And tool clearance, 100 thou, and we won't do an edge break on it. We'll go ahead and append this to the file, and there's our parting move right there. So are we ready to run this? Mm-hmm. Oh, we had an edge break. We did have an edge break in there. Well, that's okay. We'll leave the edge break in. All right. Well, we know the first part of this code is going to be okay, because we've already run it before. feeling it's a pretty hot part without any coolant on it. No, it's actually not so bad. So if we were good with our offsets here, we'd have some pretty darn close to 3/4 of an inch in diameter. Let's take a peek. Looks like we're off by 1.3 thou. So if we're going to make a couple more of these, we can go over to the offsets. So if I type in 0.0013 here, you'll notice that the text turns orange. That indicates that the value I just entered is going to make the feature that I just measured larger. What I really want to do is make that smaller. I'm going to add a minus 0.013, and that turns blue, meaning this is going to be smaller. And it's not always as easy as entering in a positive or a negative value, because a positive value on an ID tool will have the opposite effect as the positive value on an OD tool. And those are all reversed for front versus rear tool post. So that little orange-blue font in there helps you remember whether you're making the feature smaller or larger by entering in a positive or a negative wear offset. I don't think this is going to fit because we're 1.3 thou too big. We're going to make this a couple thou undersized to fit into one of those holes. Instead of 1.3, I'll give it minus 0.0, what do you think? We'll say 3.3, make it 2 thou undersized so it fits nicely into one of those holes. And we'll go ahead and run the part again. If you don't have one of these, or you're going to be making multiples of a part, it's pretty handy to use the tool itself to reposition the next rough stock, the next raw stock. So what I'll do here is I'll just say G0, rapid move, X0, Z0, right? And that'll move the machine over to the 0 position. Go ahead and use the tool itself to position the stock. Now I can go ahead and start my program again. There's the edge brake. So here we are, spot on, 2 thou undersized, just like we talked about. I guess the last thing we'd say is to actually make use of the bushing, what you do is you could swing indicate this pocket on the spindle, and then if you're going to say hold, I don't know, a drill bit or something with this bushing, you could actually chuck the drill bit itself up in the spindle and use the spindle to bore out the hole in the bushing. And then the last thing you'd want to do is slit the bushing with a slitting saw so that when you crank down on this, you end up compressing the thing that you're holding in the bushing.
Good.